energy time uncertainty. So let me give a small motivation, hand-wavy motivation, so it doesn't get us very far, but at least gives you a picture of what's going on. And these uncertainty relations, in some sense, have a basis on some simple statements that are totally classical, and they're maybe a little imprecise but incontrovertible, about looking at waveforms and trying to figure out what's going on. So, for example, suppose in time you detect a fluctuation that as time progresses just suddenly turns on. There's some waves and it just dies off after a little while. And you have a good understanding of when it started and when it ended. And there's a time t. So whenever you have a situation like that, you can try to count the number of waves, full waves that you see here. So the number of waves would be equal to number of waves or periods, number of full waves would be the total time divided by the period of this wave. So sometimes t is called the period, but here t is the total time here, and the period is 2 pi over omega. So we say this is omega t over 2 pi. Now, the problem with these waves that begin and end is that you can't quite see or make sure that you got the full wave here. So in a hand-wavy way, we say that even as we look at the perfectly well-defined and you know the shape exactly has been measured, you can't quite tell whether you got a full wave here or a quarter of a wave more. So there's an uncertainty in delta n, which is of order 1, maybe. You miss half on one side and half on the other side. So if you have an uncertainty here of order 1 and you have no uncertainty in t, you would claim that you have actually, in some sense, an uncertainty in what omega is. In a sense, omega might be well measured here, but somehow towards the end you can't quite see it. T, we said, was precise, so over 2 pi is equal to 1. I just took a delta of here and I said t is precise, so it's delta omega. So this is a classical statement. An electrical engineer would not need to know any quantum mechanics to say that's about right, and you can make it more or less precise, but that's a classical statement. In quantum mechanics, all that happens is that something has become quantum, and the idea that you have something like this, we can associate it with a particle, a photon, and in which case the uncertainty in omega is uncertainty in energy. So for a photon, the uncertainty E is equal to h bar omega, so delta omega times h bar is equal to the uncertainty in energy. So if you plug it in here, you multiply by h bar here, and you would get delta E times t is equal to 2 pi h bar. And then you have to add words. What is t? Well, this t is the time it takes the photon to go through your detector, you've been seeing it, you know, you saw a wave, you recorded it, it took a time t, began, ended. So it's a time it took you to have the pulse go through. And that time is related to an uncertainty in the energy of the photon. And that's sort of the beginning of a time-energy uncertainty relationship. This is quantum because the idea that photons carry energies and they're quantized, this is a single photon, and this connection with energy is quantum mechanics. So this is good in reasonable intuition, perhaps, and it can be the basis of all kinds of things, but it points out to the fact that the more delicate part here is T, that how could I speak of a time uncertainty? And the fact is that you can't speak of a time uncertainty really precisely. And the reason is because there's no Hermitian operator for which we could say, okay, the eigenstates of this Hermitian operator are times, and then you have a norm, and it's an uncertainty. So you can't do it. So you have to do something different this time. And happily, there's something you can do that is precise and makes sense. So we'll do it. So what we have to do is just try to use the uncertainty principle that we have, and at least one operator, we can use something that is good for us. We want uncertainty in energy, and we have the Hamiltonian. It's an operator. So for that one, we can use it, and that's the clue. So you'll take A to be the Hamiltonian, and B to be some operator Q that may depend on some things, for example, X and P or whatever you want. But the one thing I want to ask from this operator is that Q has no explicit time dependence. No explicit time dependence whatsoever. So let's see what this gives us as an uncertainty relationship. Well, it would give us that delta H squared times delta Q squared would be greater than or equal to the square of psi 1 over 2I H with Q psi. Okay, that's it. Well, but in order to get some intuition from here, we better be able to interpret this. This doesn't seem to have anything to do with energy and time. So is there something to do with time here? That is, in fact, a very well-known result in quantum mechanics, that somehow commutators with the Hamiltonian test the time derivative of operators. So whenever you see an H with Q commutator, you think, oh, that's roughly dq dt. And we'll see what happens with that. And you say, oh, dq dt, but it doesn't depend on t. Is it 0? No, it's not 0. There's no explicit dependence, but we'll see what happens. So at this moment, you really have to stop for 1 second and derive a familiar result that may or may not be that familiar still to you from 804. I don't think it was all that emphasized. Consider expectation value of Q. And then the expectation value of Q, let me write it as psi Q psi, like this. Now let's try to take the time derivative of this thing. So what is the time derivative of the expectation value of Q? And the idea being that, look, the operator depends on some things, and it can have time-dependent expectation value because the state is changing in time. So operators can have time-dependent expectation values even though the operators don't depend on time. So for example, this depends on x and p, and the x and p in a harmonic oscillator are time-dependent. They're moving around, and this could have time dependence. So what do we get from here? Well, if I have to take the time derivative of this, I have d psi dt here, q psi, plus psi q d psi dt. And in doing this and not differentiating q itself, I've used the fact that this is an operator and there's no time anywhere there. I didn't have to differentiate q. So how do we evaluate this? Well, you remember the Schrödinger equation. Here, the Schrödinger equation comes in because you have time derivatives of your state. So I d psi dt, I h bar d psi dt is equal to h psi. That's a full time-dependent Schrödinger equation. So here maybe I should write this like that. This is all time-dependent stuff. At this moment, I don't ignore the time dependence. The states are not stationary states. If they would be stationary states, there would be no energy uncertainty. So I have this, and therefore, I plug this in here, and what do we get? I h bar h psi q psi plus psi q I h bar h psi. No, I got the IH in the wrong place. I'm sorry. 1 over IH bar and 1 over IH bar. Now, first term, this thing comes out as its complex conjugate, 1 minus IH bar, because it's on the first input. H is Hermitian, so I can send it to the other side. So psi h cube psi. Second term, the 1 over IH just goes out, and I don't have to move anybody. QH is there, psi. So actually, this is I over H bar, because minus I down goes up as I. And I have here psi HQ, and this is minus I over H bar, so I get HQ minus QH psi. So this is your final result, the expectation value, ddt of the expectation value of Q is equal to I over H bar expectation value of the commutator of H with Q. So this is neat, and it should always stick in your mind. This is true. We will see the Heisenberg way of writing this equation in a little while, not today, but in a couple of weeks. But that's, you know, maybe even write it even more briefly as I over H bar expectation value of HQ. So what do we get from here? Well, we can go back to our uncertainty principle and rewrite it, having learned that we have time derivative. So time finally showed up, and that's good news. So we're maybe not too far from a clear interpretation of the uncertainty principle. So we're going back to that top equation so that what we have now is delta H squared, delta Q squared, is that thing over there, the expectation value of 1 over 2i. There's some signs there, so what do we have? Equals 1 over 2i h bar over I ddt of Q. So what I did here was to say that this expectation value was h bar over I ddt of Q, and I plugged it in there. So, you know, you square this thing, so there's not too much really to be done. The i's don't matter at the end of the day. It's a -1 that gets squared. So the h bar over 2, I'm sorry, the h bar over 2 does remain here, squared. And you have dq dt squared. Q is a Hermitian operator. B was supposed to be Hermitian. The expectation value is real. The time derivative is real. It could be going up or down. So at the end of the day, you have delta H, delta Q is equal, greater than or equal h bar over 2, the absolute value of dq over dt.